Hey guys, today we're going to look at Newton's laws of motion. We're going to look at his first law and his second law. And the first one is one we just kind of have to know generally what it means. The second one is more important though. There's some math attached to that one and it's very useful. So we'll start off with Newton's first law, which is called the law of inertia. And in this little bit, we're going to learn about what inertia is and what the first law is. Then we have to distinguish between the concepts of mass versus weight, because that actually relates to this to some degree. And also we'll see that the first law defines what forces are and what a force is. We'll start off here. We need to talk about Isaac Newton a little bit. That is Isaac Newton, in case you didn't know that already. If you would ask Isaac Newton what he did for a living, what he was to describe himself, he would say that he was a natural philosopher. He wouldn't have said he was a scientist or a physicist because those terms didn't really exist at that time. He considered himself a natural philosopher. Now, when we think about philosophy today, in the day where we live in, we think of a philosopher as somebody who thinks about big thoughts, thinks about general broad truths about humanity. Like what is the nature of good versus evil? What is the meaning of life? Big, broad questions, but pretty general and kind of squishy. That's what philosophers do. Now, in Newton's time and before him, a natural philosopher kind of did the same thing, but he talked about the natural world. So Isaac Newton was looking for broad general truths about how the world and how the universe works. And the first one of these that he came up with, first observations that he came up with, became his first law, which is the law of inertia. Short version of it is things tend to keep doing whatever they're doing. So we have a bowling ball sitting there on the floor and it's not moving. It's just sitting there. And it is going to keep on sitting there basically until the end of time. So things tend to keep doing whatever they're doing. In the case of this bowling ball, if it's moving, it's going to keep moving. And if it's not moving, it will never move ever, unless somebody comes along and pushes it. They pick it up or they kick it or they push it with a stick or something like that. It's going to stay there stationary forever and ever until a force acts on it. Conversely, if it's rolling, a bowling ball rolling down the alley, it will just keep on rolling and rolling and rolling in a straight line forever and ever until it runs into something. And when it runs into something, that something pushes on it and it changes its motion. So the formal way of saying this is that an object in motion will remain in motion and an object at rest will remain at rest until acted on by a net unbalanced force. And you may have heard those words before, but they're kind of fancy and it really boils down to this. Things tend to keep doing whatever it is they're doing. So there is a little bit to unpack here. So this inertia is the name of the game. So what is inertia? We need to define that. Inertia is a characteristic of an object that resists changes in its motion, and it's related to mass. If something has a lot of mass, it has a lot of inertia. A bowling ball is pretty heavy, has a lot of mass, and it's not going to move if you push on it very gently. A ping pong ball, though, if you push on it pretty gently, the ping pong ball will move because it has less mass, which means it has less inertia. A ping pong ball is easier to change its motion than a bowling ball. And a bowling ball is easier to move, to change its motion than a truck. The more mass it has, the more inertia it has, and the harder it is to get it to change. Now, how about this idea of an unbalanced force? You guys already know that a force is a push or a pull. First law says that you have to have unbalanced forces to make something move. So this bowling ball will stay here until we push on it. But what if two of us push on it from both sides at the same time? So we're pushing with equal forces in opposite directions. Well, those forces add up to zero. So the net force means the total force. When you add up all the forces and take into account the directions they go, if somebody's winning that shoving match, that means that there's a net force and the bowling ball will move. Okay, now that brings us to something which is kind of important to recognize here, and that is the difference between mass versus weight. Okay, mass versus weight, because in our English class and the way we use these words every day, these words mean pretty much the same thing and they're pretty interchangeable. That's in common language. In physics, they mean very different things, and it's important for you to know the difference, understand the difference between the mass of an object and the weight of an object. Okay, so how do we describe mass? Mass is stuff. I can think of no better way to describe it. It's the stuff that an object is made of. So if you have a bowling ball, it's made up of a whole bunch of protons and neutrons and electrons that are all together in a nice, neat package. There's stuff in there. Now, if I took the bowling ball to the moon, it would still have the same amount of stuff. It would still have the same amount of mass because there's the same protons and neutrons and electrons in that ball, no matter where I take it. The mass never changes. Okay. Now, the units of mass are kilograms. Okay. There's a little bit more on mass, but we'll get back to it. Now we want to talk about weight. So if I pick up the bowling ball, it'll make my arm tired. If I just try to hold it at arm's length, it's going to be very difficult to do, and my muscles are going to get tired. Eventually, I'm going to have to drop the thing. And the reason that my muscles get tired is because gravity is pulling on that bowling ball, and it's pulling it down toward the ground. And that force of gravity acting on the bowling ball, that is the ball's weight. Okay? So the units of weight is a force caused by gravity. The units are newtons, which you may recognize as the units of force, push or pull. But the thing about weight is that it depends on the gravity where you are. So if I take the bowling ball to the moon, it's not going to have as much weight because there's less gravity on the moon. It's going to be easy for me to hold it up for a long, long time because there's just no gravity pulling it down. So the mass of the ball stays the same. It still has as much stuff, but its weight changes because the local gravity is different. Okay, so to finish up here with mass, the mass of an object is the same anywhere in the universe where we take it because the amount of stuff in the object never changes. Weight does change because it depends on the local gravity. So that's mass versus weight. Okay, let's see. Let's move on now to the second law, Newton's second law. Here we go. Newton's second law is the most commonly used of Newton's laws. There's a math equation that goes with it. It's a pretty simple one, but there is some math. We can actually hang numbers on this and make predictions about how the universe is going to behave, which is very, very useful. So we'll talk about what it means with the equation, then we'll run through a couple examples of it. Now, we have actually already seen this. The second law. We've introduced it before, though you may not have realized it. The last exercise we did when you were doing the physics classroom simulation, online simulation, to see how objects accelerated under different forces, you were discovering Newton's second law. So here's what it looks like in math. Okay, now first off, what you discovered in the activity last time was that acceleration is inversely proportional to mass. What does that mean? Okay, it means that if you have a large mass and you apply a force to it, it's not going to accelerate very much. Whereas if you have a small mass and you apply the same force to it, it accelerates a lot. So this is the way it looks as an equation. That squiggly equals thing means is proportional to, and we say acceleration is inversely proportional to mass, meaning that if we take the inverse of mass, 1 divided by the mass, that tells us the acceleration. So if m is a great big number, well, 1 divided by a great big number is a little tiny number, which means we get a small acceleration. Whereas if m is a little tiny number like 1/100th or 1/10th, 0.001, something like that, when we divide 1 by a little tiny number, we get a great big number. So that's what we mean by acceleration is inversely proportional to mass. Now, you also discovered that if you push harder, the thing accelerates more. So that means that acceleration is directly proportional to force, meaning that a large force makes a big acceleration, and a small force makes a small acceleration. So when one gets bigger, the other one gets bigger too. Whereas when you're talking about mass, when mass gets bigger, acceleration gets smaller. That's what you discovered last time. Now, Newton put these together, and he said in his natural philosophy kind of way, well, this is generally true, the things that you just figured out yesterday, but we can put them together and make a single equation out of them and say Well, acceleration is directly proportional to force and inversely proportional to mass. So you could say that it's proportional to force divided by mass. That's what those symbols mean. Now, the leap that Isaac Newton took, and this was revolutionary, was to say maybe this isn't just a kind of, sort of, generally speaking, naturally philosophy kind of thing. Maybe this is a hard and fast rule. Maybe if we can hang numbers on these things, this relationship will always be the same for everything in all situations. So maybe instead of a proportional sign, maybe we could make an equal sign here. And if we rearrange that, we can say F is equal to MA. So we multiply both sides by M, we get F equals MA. And you may recognize that as Newton's second law. If you don't, you need to recognize it now because it's one you need to know. It's an integral part of this class. Now let me show you how this all works here. There are some variables and such, so we're going to write some of this stuff down, then we'll do a couple examples here. Okay, so F equals MA. That is Newton's second law. Newton's second law. That's what it is, Newton's second law. All right, force, as we saw before, is always measured in newtons. Newtons of force, abbreviated N. M is always the mass of an object, and that is always in kilograms. And A is the acceleration of that object, and that is always going to be in meters per second squared. Okay? This is the way it usually shows up in books and on worksheets, but a more sensible, intuitive way to write it is the way we saw it originally, which is A is equal to F divided by M. And the units are all the same of these units. But what it says is if you have a mass and you apply a force to it, you're going to get an acceleration. These are what they are. This is what you kind of put into an experiment. This is what you test, and some acceleration is going to come out of it. So acceleration is the dependent variable. It depends on the value of these other two. So a lot of students find this to be more intuitive, but it amounts to the same thing. Okay, so suppose we have a mass of 25 kilograms, okay? Mass of 25 kilograms, and we push on it with a force of 100 newtons. We want to know what's the acceleration, okay? So acceleration is equal to F divided by M. That's what we see over here. So we get acceleration is equal to 100 newtons divided by 25 kilograms, and we wind up with 4 meters per second squared. That's the answer. So Newton showed that we can plug numbers into this equation and get predictable results. Now, what if we increase our force? What if we increase the force to 200 newtons? Okay, what do you think is going to happen to the acceleration? You can probably make a prediction on this, but let's see. So acceleration now is going to equal 200 divided by 25 kilograms. And if you need a calculator for this, that's fine. 200 divided by 25 equals 8. 8 meters per second squared. So if we double the force, go from 100 newtons to 200 newtons, we double the acceleration. Twice as much force equals twice as much acceleration. That's what you saw last week. Now we can also, what if we change the mass? What if we keep our 100 newtons here, but we change it to 50 kilograms? Okay, now we're going to have 100 newtons divided by 50 kilograms, and we get 2 meters per second squared is our acceleration. So if we double the mass, we cut the acceleration in half. Now let's see if the same thing happens with the bigger force. We had 200 kilograms, and again, we're going to divide it by 50 kilograms. 200 divided by 5 is 4 this time, 4 meters per second squared. And again, if we double the mass from 25 to 50 kilograms, twice as much mass, we get half as much acceleration. And that's what you found last time as well. When we double the mass, we get half the acceleration. If we triple the mass, we get 1/3 the acceleration. We get 10 times the mass, we get 1/10 of the acceleration. Whereas if we increase the force, if we double the force, twice the acceleration, 10 times the force, 10 times the acceleration. And that's the relationship that comes out of Newton's second law, F equals ma. Okay, you're going to have a few practice problems to do with this on a worksheet, and we will see you next time.